Welcome to our discussion of Chapter 2 on probability. This will be part 1 of the series. We'll be discussing sections 2.1 to section 2.3, and this will cover the introduction to sample spaces and events. To start, we're going to introduce a little bit of terminology. An experiment will be a process of observation or measurement, and the result of any kind of experiment will be considered an outcome. And we also have a couple different ways of viewing probability from the start. The sort of classical definition relates to when we're given n equally likely outcomes and k of them are considered favorable outcomes, then the probability of the event in question is considered to be k over n, where we take the favorable outcomes and divide by the total number of outcomes. So the classic example of this is, say we flip a fair coin. There's two possible outcomes, a head or a tail, but if we're interested in the probability of getting a tail, then there's only one way to do that out of the two total outcomes, so the probability is equal to 1/2. Another way to view probability would be the relative frequency interpretation. This is when we define probability to be the proportion of times an event happens in the long run. And an example of this might be if we were to be able to look up records of weather and discover that in Lewiston on January 1st, 75 times out of the last 100 years, there was snow, then we would say the probability of snow on January 1st is 75 out of 100. So let's revisit the idea of classical probability by way of an example. Say we flip a fair coin 3 times and we're interested in determining the probability of getting exactly 2 heads. To start, we might think about counting the total number of possible outcomes using the strategies that we learned in Chapter 1. If we're thinking in terms of slots, then for the 3 slots there are 2 options for each. So we get 2 to the 3, which is 8 possible outcomes. Now we might take it one step further and list all of those outcomes: heads, 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 head, head, tails, head, tail, head, tail, head, head, and so on. Once we list all possible 8 outcomes, then we just go and we determine where we find the ones we're looking for, in particular the ones where there are exactly 2 heads, no more and no less. There are 3 of them out of the 8. So using that classical probability definition, we take our 3 favorable outcomes divided by the total number of 8 outcomes to get a probability of 3/8. The set of all possible outcomes of an experiment will be called the sample space, and we'll denote it with an S, and each outcome in the sample space is also considered an element of this set S. So for our purposes, if S has finitely many elements, then we can do the kinds of things that we've done so far in examples that we've done in Chapter 1. We might actually list all possible elements to count them to have a sense of how many there are. But in some cases, S is going to have a large number of elements, or there will be infinitely many elements. In both of those cases, in the case where it's just a finitely large number of elements, it's going to be prohibitive to try to list them. And if we have infinitely many elements, then we certainly can't list them. So in those cases, we're going to use words or mathematical rules to describe the elements. So for example, I might define a sample space to be S, which is the set of elements x, where x is equal to 2k for some integer k. And our interpretation for that is going to be that x is going to be some sort of an even number because it's of the form 2k. So S here consists of the set of even integers. I might also add at this case that S is going to be considered discrete if S consists of a countable set of elements. So countable will be either a finite number of elements or an infinitely large number of elements where we can set up a one-to-one correspondence with the whole numbers. By contrast, S will be considered a continuous sample space if it consists of an uncountable set of infinitely many elements. So that might be a scenario where S represents a set of outcomes from some sort of measurement of a physical property, such as something like temperature or length, things that are measured on a continuous scale. Next, we define an event, which is a subset of a sample space, so we'll sort of flesh this out a little bit through an example. Suppose we flip a fair coin 4 times, and we'll define 3 events as follows. The first event will be A. This is the case where we get 0 heads in 4 flips. Event B will be the case where we get exactly 1 head in the flipping of 4 coins. And the third event, C, will be the case where we get exactly 2 heads out of the 4 flips. And our next step might be to start counting the outcomes in each of those events to figure out how many there are. So if we're thinking about, I've got 4 coins which we're flipping and I want none of those coins to come up heads, it should seem reasonable that there's only one way for that to happen, in particular the case where we get 4 tails. We could also think of that as taking the 4 flips and choosing 0 heads out of those 4 flips. Likewise, when we want the case of exactly 1 head, we could be taking those 4 flips and choosing 1 head, so turning that into a combination is 4 choose 1. And similarly for event C, where we get exactly 2 heads, we take the 4 flips, pick 2 of the flips, choose 2 of the flips to be heads, and there are 6 ways for that to happen. So then, if we think about flipping the fair coin 4 times, there should be 2 to the 4 or 16 possible outcomes, and we can now compute probabilities. The probability for event A occurring would be 1 out of 16, for B 4 out of 16, and for C 6 out of 16. Now let's define some new events. These will be considered compound events because they're based on other events. Say we have events A and B, which are subsets of the sample space S. We can define a new event to be the union of A and B. And this is the case where we take all of those elements in A and all of those elements of B, and we sort of toss them together in one big pot. So the union of A and B is the set of all x values where x is either in A or in B, or potentially both. We can use what's known as a Venn diagram to represent this. A Venn diagram is a diagram where we initially set a box. This rectangular box in particular represents the entire sample space, and then inside the box we put circles or some sort of geometric shape to represent an event. And in this case, we're drawing 2 circles, one for A and one for B, and we're allowing those 2 circles to overlap to represent this possibility that A and B could potentially share outcomes. So A union B is going to be represented by this shaded region here that's in green, where we have all of the circle of A shaded as well as all of the circle of B. The next compound event is the intersection of A and B. In this case, we're looking for only those elements in the sample space that are both in A and in B, so namely that's exactly where the 2 circles overlap. And the next event that we're interested in is called the complement, so we'll use a prime notation to represent a complement, so A prime will also be called a complement. And this consists of elements of our sample space that are not in A, so everything outside of A, which is why that's the region that's shaded in this Venn diagram. In addition, we might say that A and B are considered mutually exclusive or disjoint if their intersection is empty. So that means those two circles inside the Venn diagram won't overlap because they don't share any outcomes in common. And we'll also say A is going to be considered a subset of B if every element of A is also contained in B. So in the case of our Venn diagram, we want the circle that represents the event A to be contained entirely inside the circle that represents B. And then we can talk a little bit more about being mutually exclusive or disjoint, but now we'll talk about it in the case of multiple events, and this extends beyond just 2 or 3 events, but we'll just do the example for 3. We'll say that events A, B, and C are disjoint if the intersection of A and B and C is the empty set, so A intersected with B intersected with C. Whereas we'll say they're pairwise disjoint, those 3 events, if when we look at any pair of those 3 events, if we look at the intersection of any pair of those 3 events, we get the empty set. So A intersected with B is empty, if A intersected with C is empty, and if B intersected with C is empty, then we'll say those 3 events are pairwise disjoint. We require all 3 of those conditions for pairwise disjoint. So now let's look at a couple of ways that we can use Venn diagrams to help us. So the first will be an example that's a bit of a sort of a mathematical argument by means of the Venn diagram. So in this case, we want to show that 2 compound events are the same. The first will be the union of A with the intersection of B and C, and the second thing that we're comparing it to is going to be the intersection of the union of A and B with the union of A and C. And the argument here is that these 2 things are equivalent, and we can use Venn diagrams to show it. So we'll just consider the first one at this point, this union of A with the intersection of B and C. So to start, we draw a Venn diagram that just represents the first part of that union, event A. So we have 3 overlapping circles because we have 3 events of interest, and we'll shade the region that represents A. Then we'll go to the second part of the union in this statement, which is the intersection of B and C. So now we draw a separate Venn diagram where we shade only the region shared by B and C to represent their intersection. And now we're interested in the union of these two sets, so we look at these two Venn diagrams and we say, okay, if this is the union, then we want to take everything that's shaded in the first picture and combine that with the stuff that's shaded in the second picture to get our outcome. So the union of A with B intersected with C is this shaded region here, all of A plus that bit where B and C overlap. So now our argument is to show that that's equivalent to this second statement, which is the intersection of A union B and A union C. So we'll start again with two separate Venn diagrams, the first of which represents the union of A and B, the second of which represents the union of A and C, and we're looking for the intersection of these two Venn diagrams. So then that means we're looking to shade in our final picture only the regions that are shaded between both of these two here. So namely, all of A is shaded in both, and then this little section here where B and C overlap is shaded in both. But over here, this section of C is not shaded in both, nor is that particular section of B in the first Venn diagram. So these areas where I put little red X's won't be shaded in the final picture. And when we do shade our final picture, we discover that the two diagrams for the two different expressions are the same, and therefore they must be equal. We can also use a Venn diagram to help us count things or to determine probabilities. So let's start with an example where we have a sample space that consists of 200 students, of which 138 are enrolled in psychology, 115 are in economics, and 91 students are enrolled in both. And now we're interested in answering a variety of questions, maybe something like how many students are not enrolled in either, or perhaps what's the probability that a randomly selected student is in econ but not psych. So we want to answer those questions, but to start, it's not exactly easy to determine that information from the way things are expressed. So what our job is then is to sort of use this Venn diagram to help us. We'll start by noticing that 91 students are in both, so they're in the intersection. We'll label that with a 91. And we know that there are 115 students in economics, so if we take 115 and subtract the 91 students that are in both psychology and economics, we're left with 24 students left over. So that 91 plus the 24 have to give us the total of 115. And then similarly, we've got 138 total that are enrolled in psychology, but we know that 91 of them are also in economics. So if we take the 91 and subtract it from the 138, we get 47 people left over in this other portion of the P circle. Now, if we add up these three numbers, it doesn't equal 200. In fact, it's less than 200. And that means that there are some extra people hanging out in the outside, namely 38. These 38 people are the remainder of the students out of the 200 that are not in probability or economics, or possibly both. So now that we've got this Venn diagram with the regions labeled with the counts of people per each region, now we can answer these questions. Suppose we want to describe in words the event E prime. Well, remember for us, E prime refers to the complement. That's anything that's not in E that's also in the sample space, namely this 47 and this 38. So E complement will be any student out of that 200 that's not in economics, and there are 85 out of the 200 students, so that's our probability. Next, we're interested in the number of students that are not enrolled in either probability or economics. That's just the 38 people sitting out here in the rectangle but not inside the circles. So 38 students are in neither psychology nor economics. And then lastly, what's the probability that a randomly selected student is in econ but not psych? Well, students that are in econ, there's 115 of them, but 91 of them are also in psychology, so that means only 24 remain in economics but not psych, and since we're looking for a probability, we'll take this 24 out of the total of 200. And you'll notice here that I've used a little bit of set notation, E intersected with P complement to help reinforce what we've done. So P complement means people that are not in psychology, and we're intersecting that with the people that are in economics. Namely, that just gives us that 24 out of the 200. This concludes our discussion of sample spaces and events. Thank you.